In previous period, we have derived this equation for depression of a beam loaded at free end. That equation is dy by dx equals to dy by dx equals to w upon y into iz into lx minus x square by 2 plus k1. Up to this step, we have calculated or derived this equation in the previous period. Here in this equation, k1 is the integration constant, where k1 is the integration constant. And to calculate the value of k1, we know that at x equals to 0, means the distance of the beam x equals to 0 means at point A where the beam is fixed, there means that is at A, the depression is 0. The depression is 0. Therefore, theta equals to 0. That is tan theta equals to dy by dx equals to 0. It means that therefore the value of k1 equals to 0, and equation 4 becomes dy by dx equals to w upon y into iz into lx minus x square by 2 plus this is that equation. Here the value of k1 is 0. Now to find the value of y or the value of integration, we have to integrate this equation once again. Now integrating equation number 5 once again with respect to x. Now integrating equation 5 with respect to x, we can have means taking the integration dy by dx into dx equals to integration of w upon y into iz into lx minus x square by 2. Here, for integrating this equation, we have to take the constant term outside the integration sign. Therefore, here this equation of left hand side is only y equals to the constant term is w upon y into iz into lx square by 2 minus x cube by 6 plus k2. Once here, this k2 is also an integration constant. Now this to calculate the value of k2, we know that at a x equals to 0, that is at a the depression is 0. And therefore putting the values of x equals to 0 and theta equals to dy by ds equals to 0. Therefore, the value of k2 is also 0. Now, therefore, the value of k2 is 0. Now, this equation becomes y equals to w upon y into ic into lx square by 2 minus x cube by 6. This is equation number 6. And this is the equation of a depression at x from A. This is the equation of depression at distance x from A. Now, to calculate the depression from B to B dash, when load is suspended at its free end, means to calculate the depression, hence depression of a bar, hence this is the, we write it in details, this equation, or this is the equation of depression. This is the equation of depression at distance x from A. Now, to calculate the depression from B to B bar, or to calculate the depression of B, depression of B from B to B dash. Now here what we want to do, here the length of the beam is L, and therefore we have to put in place of x, we have to put L. Therefore this equation becomes, now therefore putting or substituting, calculate the depression. Now to calculate the depression of beam B to B dash, substitute x equals to L in equation number 6. X equals to L in equation number 6. This gives us y equals to w upon y into ic into L into L square upon 2 minus L square upon 6. This is not L square, this is x cube. X cube upon 6. Now, here we solve this equation and write it in simplified form like this: y equals to w upon Young's modulus y into ic into L into L is L cube upon 2 minus L cube upon 6. That is w upon y into ic into 3 L cube minus L cube upon 6, taking the LCM. Here this equation is y equals to w upon y into ic into 2L cube upon 6. That is equals to y equals to w upon y into ic into, or here we write here 2 by 3 into L. This is the equation of depression of beam This is the equation of depression of a beam when a load is suspended at its free end. Now we want to calculate. We know that if the bar is a rectangular, if here in this equation this is the Young's modulus and this is the geometrical moment of inertia. Suppose if the bar is a rectangular, bar is having the rectangular cross section area, then this geometrical moment of inertia Ig equals to can be written as here the cross section of the beam is a rectangular, means it is having a breadth and a thickness, breadth B and thickness D. Therefore, its geometrical moment of inertia then is given by B into D square upon 12. This is the geometrical moment of inertia. Putting this value in this equation, we write y equals to 2 by 3 into W upon Young's modulus into geometrical of moment of inertia, and its value is B d cube square upon 12 into L cube. Now I write here y equals to directly write this is in this type 12 WL square upon 12 WL square upon 3 y dt square, that is equals to be 4 WL square upon y bt square. And this is the equation, or with the help of this equation we can calculate the depression of a beam whose cross section is rectangular. Now suppose the cross sectional area is circular, means the beam is a bar type or it's circular. It's therefore if the beam is having cross sectional area if beam is having cross sectional area circular cross section, beam is having circular cross section area, then geometrical moment of inertia is given by Iz equals to pi r raised to 4 upon 4. Putting this value in the previous equation, we can calculate the depression of the beam, that is the depression of beam can be calculated here in this way: W upon y into the value of the geometrical moment of inertia, that is pi r raised to 4 upon 4 into pi r raised to 4 into L cube upon 3, L cube into L cube by 3 into L cube by 3. Here in this equation it is also L cube. Here it is also L cube. So now we simplify this equation. Lastly, we get the equation of this type. That equation is y equals to 4 by 3 WL cube upon y into the value of geometrical moment of inertia, that is pi r raised to 4. With the help of this equation, we can calculate the depression of beam when the bar is having the circular cross section area. And with this we have finished the point cantilever loaded at free end. Now in the next period we will see the next assumption, that is the weight of the beam is effective. That part we will discuss in the next period.